Welcome back to the final chapter of the part of this lecture that discusses calculus in one variable, namely the chapter integration. We want to discuss integrals of functions, and most of you have already seen integrals in high school, I assume, but we will do the construction completely from scratch, and we will redo everything, including proofs this time. Okay, so before I give you the definition, I will give you the motivation for the definition, and the motivation is kind of now a geometric one. Assume we have some function defined on a closed and bounded interval from this interval AB into the real numbers, whose graph I've drawn here. So AB is some interval along the x-axis, and this is the graph of f. Okay, what we now want to do is we want to compute the area, the area of the following shape, the shape of all points below the graph, or in this case between the graph and the axis here. By which I mean if I draw a vertical line here and a vertical line there. Whoops, sorry. This is not really a line. Yeah, something like this. I'm interested in this area here. So that is called this AF. So what is the area of AF? We want the area of AF, which is defined as, formally, this is the set of all x and y in R2, where x is somewhere in the interval AB. Whoops. And y is in the interval 0 to f of x, and this indicates that f of x is bigger than 0 for all x. Whoops. Okay, so if we would be negative, we have to be a bit careful with the definition, but this is enough for now. But the idea is kind of how can we get this surface area? And the idea would be if we would be below this, below the x-axis, we want to count the surface area between the graph and the x-axis as well, but with a different sign. So we kind of want the total net surface area of this region here below the graph. So the idea is, now if we do this, and this is now really only geometrically intuitively, I will do this more precisely in a moment. The idea is kind of, we don't know how to compute the surface of such a complicated thing, because f might be anything. But the idea is we want to approximate this by some areas, by some subsets of R2, whose areas we can indeed compute. And the idea is the kind of most basic thing, the most basic shape in R2, whose area we can compute, is a rectangle. The area of a rectangle is just a product of the two sides. And if we have a union of two rectangles, which is not intersecting, then we can just add the two sums and get the area of this union. So we can compute areas of unions of rectangles. And the idea is now really to take this shape and approximate this by unions of rectangles. So let's write this down. So the idea is approximate AF by unions of rectangles. Then compute the area of these unions. And then we have to kind of make precise of what it means to get closer and closer to the graph. And this is what I want to do in the picture before I continue the sentence. So the idea is the following. I will draw two pictures. So assume this is, again, the same graph as before. So something like, and here we have the interval AB and the similar graph here. I hope this looks halfway similar. It's a bit, should be okay. So the idea is now to find convenient rectangles. And the idea is now how to find these rectangles. So first of all, we kind of divide this interval AB into little parts. So let's say we put some points in between, somewhere, so not after a fixed scheme, and I do the same thing twice. So here I want the same, roughly the same, okay, should be halfway okay. And the idea is now, take rectangles that have this as one side and then go into the graph. And so let me draw some vertical lines like this, and on the one side, so it's kind of where to stop. So on this side, we take all the rectangles so that we stay below the graph here. So here we cannot exceed the graph, so we would have to take this horizontal line here. So this would be kind of the biggest rectangle, having this as a side which is below the graph. And the same we do for every of these parts here. So we go up until we are kind of still below. And do this again, and the same we would do here. Whoops, here we would take this one, and here it's this one, and so, oops, and so on. Yeah, okay, here it's. And finally, this one. So here we see we can compute the area of this union of rectangles, and we will see that kind of we are close to the volume of to the area of this area below the graph, but we will be below because there are some parts missing here, and we have chosen these yellow rectangles such that we always stay below the graph. Now we do the same thing differently. Namely, we make the same principle. We take rectangles, but this time we go a bit higher. We get to the smallest rectangle with this side, which still touches the graph here. So we take, this time as a value, the biggest value that we have that f takes in this interval, so to say. So here it would be like this. Here, yeah, similar. Oops, that was a bit much. Like this, and of course here these sides as well. Finally here. And yeah, here we go. So now we have some rectangles whose union is also, the area of this union is also close to the graph, but it will be bigger than the surface below the graph because we just are slightly above the graph. So the idea is now, of course, to approximate this. And approximating here means a simple thing. We just have to take more and more rectangles. We have to be more precise. We see if the rectangle is, has a very long side or relatively long side. We see that there's a lot of area missing. So we can just simplify this by just adding additional points in here. So we need to take thinner and thinner rectangles. That's the idea here. So take thinner and thinner rectangles. And we can then take more and more rectangles. So just these points here, by which we divided the interval, this we just have to increase the number of points and take more and more and more, so it becomes thinner and thinner and thinner, and this is the way, and then we need some kind of limit procedure, or we need kind of to get thinner and thinner and infinitely thin in some sense to approach this area. And the idea is kind of now, what should be the reasonable amount, is that if we do this procedure and get thinner and thinner, and do this procedure where we're slightly above and get thinner and thinner, that we should get the same value in the end. So then this surface area makes sense, otherwise it's kind of hard to tell what's the right value. This is an example of what we will call a lower sum of f. And this is what we will call an upper sum. The surface area of these of these rectangles. And I will make this precise on the next blackboard. But this is the idea. So this is what we want to do, and now we have to do this formally correct. Okay, let's start doing so. So the first thing we need to formalize is this kind of partitioning the interval AB into smaller intervals. There are several ways to do so, and I've decided to use a particular formalism here, which is the kind of the most convenient. So assume we have some A, B, and R with A strictly smaller than B, so we can really discuss about the interval AB and have an interesting interval. Part A of the definition, a finite family of values of numbers, x0, x1, going to some xn, of real numbers with the following property. So this should be kind of the positions of the long sides of the rectangle. So these white marks that I put in here. So these should be encoded by such numbers. So we want that they lie between A and B, and we want an ordering. We want that A is equal to x0, and that x1 is bigger than or equal to x0, that x2 is bigger than or equal to x1, and so on, until xn, and xn is supposed to be B. So this is kind of some positions between A and B. I've written family here, not set, and I've used these parentheses here instead of the set brackets because it's not only the set, but we want to preserve this order. So they should be ordered. That's important. And in the set, there's no ordering a priori way. But this is just, if I write it like this as a tuple, this just means that they are sorted by a value. Okay. So such a finite family is called a partition of AB, and we put just some notation, this curly P, so some old, I don't know how this is called, of AB is defined as the set of all, sorry, this doesn't fit in here anymore, the set of all partitions. So with n arbitrary, so that's just some number of points in between. So P of AB is defined as the set of all partitions of AB. Okay, now for the procedure of getting thinner and thinner, this basically means we need to take more and more of these markers and to take thinner to get these rectangles. So given some fixed partition here, we need to make the partitions finer and finer, so to say. And to do this formally, to say what a finer partition is, I introduce the following term. So assume we have two partitions. P consists of the values x0, x1 to xn. And we take P prime, which is y0, y1 until ym. So m doesn't need to have to be the same value. These are partitions of AB. And we say that P prime is a refinement of P if, and we just want that all positions of, that this kind of contains more points than P, but contains all points, all these markers here given by P plus some additional ones. So it just has more and so makes finer rectangles. That's what we call this a refinement. And formally this just means that every element of this partition is somewhere inside here. So if xi is an element of the set y0, y1, ym for all I between 0 and n. So every point in here is somewhere in there. That's a refinement. Sorry. Now, another term, if we have two different partitions, we say that another partition, P, that's P1, P2, and P2 and P be partitions. We say that P is a common refinement of P1 and P2. If P is both a refinement of P1 and of P2. So it needs to contain everything from P1 and everything from P2, and both a refinement of P1 and a refinement of P2. And it's kind of easy to think about this. I won't write this down explicitly, but any two partitions have a common refinement. If we just have the markers of one partition and the markers of two partition, we just take the union of everything and form a new partition containing both. So this is easy to see. So such a common refinement always exists, right? So this is something easily thought about. Okay, now we get to the upper and lower sums. So I will start with the upper sums, so with this notion I've sketched here. So we take all the rectangles, the kind of the smallest rectangle that fits above the graph in there, and this has the following description. So the area of this has the following description. We take f from a, b to r. First is some arbitrary function. We just assume that it is bounded. Otherwise, the following definition could be a mess. And we take P to be a partition, and we denote it by x0, x1 to xn, be a partition of the interval AB. Then the upper sum of f over P is the following. We denote this by UFP, and this is defined as the sum. And now we have to take the areas of these different integrals here, of these different rectangles here, sorry. And here, of course, the length of the small sides here that are on the x-axis, this is now the difference between two neighboring points in the partition. This is the length of this one side. So the one, we need to take a sum over the whole partition. So sum from j equal to 0 to n minus 1. And the one side, so I leave some space here for the other side, the one side would be xj plus 1 minus xj. This is the length of the one side. Now the other side, what's the height of these rectangles here? So the height of these rectangles would be kind of so we want to take the smallest rectangle that fits on top of the graph. This means that the height is the biggest value that f takes on this interval. The biggest value, or in other words, the supremum. So the value is the supremum of f of x, and now x is somewhere in the interval xj to xj plus 1. This is the area of the union of these rectangles. Okay, this is the upper sum. Oh, sorry, this looks terrible. This looks terrible as well. Anyway, this is the upper sum, and so now if you see this, it's kind of obvious how to define the lower sum. There, we want them to fit right under, so we need the smallest value of f that fits, that's kind of on this interval, this part of the partition, and to sum them all up. And this is what we'll do next. Let me quickly erase, and then I'll give you a definition of the lower sum, which is very similar to this one. So, given the definition of the upper sum, the definition of the lower sum is very similar. So the lower sum of f over p is denoted by LFP and is defined as the sum, and again we need to take the areas of the rectangles. We go from 0 to n minus 1. So the short side of the rectangle again has length xj plus 1 minus xj. And now for the long side, the height of the rectangle. So we cannot cross the graph of f, so we need to stay below. And here, instead of the supremum, as we did in the upper sum, we just take the infimum of f of x, where x is in the interval xj plus 1. So this sum here, oh sorry, this is really poorly written. xj plus 1. So this is the definition of the lower sum. Okay, so let me insert a theorem with some properties of lower sums and upper sums. Again, A, B are in R with A smaller than B. And we fix some partition of the interval AB. First of all, the lower sum of f over p is smaller than or equal to the upper sum of f over p. And B, this is more interesting now, if there's a second partition, p prime is a refinement of p, then the lower sum of f over p is smaller than or equal to the lower sum of f over p prime. And for the upper sums, it's precisely the other way around. The upper sum of f over p is bigger than or equal to the upper sum of f over p prime. Let me draw a very simple picture where you can just, we'll see some examples, so we don't take the full real line, just take one part of the partition here. So here's, let's say here's some xj and here's some xj plus 1. And the part of the graph that's above this is maybe, I don't know, something like this. Okay, and if we now take the lower sum, this is with respect to all rectangles that fit below here. So the lower sum with respect to this partition, the part over this thing would be this rectangle here plus some others. But if we now would refine this, this means inserting new points. So assume we add some point here in the middle and take now this as part of the partition. Then here we would take the lower sum on this interval here. This would be basically a part of the same rectangle here. But on this interval, we can take different values because here this is not longer relevant. We only need to consider the values of f over this smaller interval. And in this case, this is a bigger rectangle. So in this case, we can take this rectangle. And of course, the surface area of these two rectangles is bigger than the surface of this small one. So simply because so refinements mean more precision. In the same way, the upper sum, this would be then the rectangle that is part of the upper sum in here would be this big rectangle would be, yeah, something like this. So this big rectangle here would be the part of the upper sum of the partition P. But if we insert this new thing here, here we would still take this pink rectangle here. And here, over this part, we only need this supremum over this interval, which would be somewhere here. So here we would take this pink rectangle. So here it would be the union of the areas of these two pink rectangles, which is smaller than the big union here. Now there's too many colors in between, but anyway. So here you can see that's why more refinements give more precision, and this means kind of that these rectangles are then closer. So yeah, more precise, so to say. Okay, but now this needs to be formally proven. So first of all, the first part is obvious. This is basically because the infimum of a set is smaller than the supremum of, smaller than or equal to the supremum of a set. So let's say this is obvious. So just putting the two definitions next to each other. So for part B, we let P, we just make notation for the points of the partitions from x0 to xn. P prime, the refinement should be y0 to ym. And so for each j between 0 and n, we have some index such that xj coincides with one of these. So we have some k index j between 0 and m with xj is y kj. Okay, so with y kj for all j. So this is definition of the refinement. Then, if we just write down the lower sum formally, so I would only do the computation for the lower sum, the upper sum is analogously. So then, LFP, this is by definition the sum of j from 0 to n minus 1, and then the infimum of f of x, where x is between xj and xj plus 1, times xj plus 1 minus xj. Okay, now in this terminology, we can refine this, we can rephrase this as follows. This is the same as the sum j equal to 0 from n minus 1 inf of x between y kj and y kj plus 1. So j plus 1 in the index, sorry, I hope this is readable, f of x times y kj plus 1 minus y kj. Okay. This looks more complicated than it is actually, because now we can kind of describe these differently. Here there's the difference between two elements of the partition that are not particularly or not necessarily next to each other. There might be other points in between, but the sum of this long part between these two points of the partition is the same as the sum of the individual parts in between. So this is then technically, this is this, sorry, let me start here. This is the same as the infimum, sum j from 0 to n minus 1 over the infimum of x between ykj and ykj plus 1 f of x times, and now the sum, I going from kj to kj plus 1 minus 1 yi plus 1 minus yi. If you take a look at the sum, this is the telescopic sum. So as a telescopic sum, with this, the sum of these things just becomes this sum. So this basically means that the long part of the partition is the sum of the individual small parts. Okay, this is now, we can now reorder these things by putting the sum in between. So basically multiplying each summand with this here. So this means this is the sum of j from 0 to n minus 1, sum from I equal to kj plus 1 minus 1, inf x in ykj plus 1 times yi plus 1 minus yi. Okay, and at this point, this is basically by an old exercise about infimum and supremum. Sheet 2, exercise 1. It holds for all, I will say momentarily what this is about, for all j between 0 and n minus 1, and then all I between kj plus 1 minus 1, we get the following. That's the infimum of x in ykj plus 1 f of x. Now, if we consider the interval yi plus 1 for I and j chosen like this, this then means that the interval from yi to yi plus 1 is contained in this bigger interval. Oh, there's a j missing, kj plus 1, almost unreadable, sorry. So we take a subinterval, but if we restrict to a smaller set, and this is now where this exercise is kicking in, if we restrict to a smaller set, the infimum of the set becomes bigger or equal. But there might be that the points which kind of pull the infimum down are left out when we take a smaller set. So this is indeed smaller than or equal to the infimum over all x in yi plus 1 f of x. Simply because of the subset property. If we take the infimum over a smaller set, it might become bigger. The same way, if we would have the supremum here, if we would take a smaller set, the supremum could become smaller or equal, but not bigger. But this is the general inequality here that holds for the infimum. And so if we insert this in here, and so for each of the summands, we replace this interval by the corresponding yi, we get that LFP, which is this, is bigger than or equal to the sum of all j from 0 to n minus 1, the sum of all I from kj to kj plus 1 minus 1, infimum over all x in yi plus 1 times f of x times yi plus 1 minus yi. And if we just take a look at this sum, this is just an unnecessarily complicated way of just summing up all the yi and yi, so going from I from 0 to m. Namely, this is the same, if you just take a look at how the sum is built, this is the same as the sum from 0 to m minus 1 over I for inf x in yi plus 1 f of x times yi plus 1 minus yi. But if you take a look at this, this is precisely the definition of the lower sum of f over p prime, since p prime is defined by these yi's. So this shows the inequality we wanted. So this is basically just this very simple idea that I sketched you in this, okay, there's not too many colors in there, but that I sketched in this diagram. And this is basically just a formal calculation which kind of does this, but in this general way. yeah, the same thing. Analogously, you could handle the upper sums, so you just need the supremum instead of the infimum and do the same arguments. Analogously, one shows the other inequality, so u of fp is, sorry, no, it's wrong way around. U of fp is, what? Oh, sorry. My mistake, my bad, sorry. This is then bigger than or equal to. Here I just have the wrong equality, I'm sorry. I've replaced this by the bigger infimum everywhere. Sorry for if there's any confusion. So this shows that L of fp is smaller than or equal to this. Sorry about that. And for the inequality, for the upper sums, it's just the other way around, since this inequality is then the other way around. For the suprema, so we get that this is bigger than or equal to u of fp prime. Sorry, I was just confused for a second. Okay, let me erase, and now we come to the definition of integrals. Let's go towards integrals. Definition 5.3. So same setting, we have a, b, and r. A smaller than b, and we have a function from a, b to r, which is bounded. Okay, so we want to define the so-called upper integral with the help of upper sums. The upper integral of f so assume we take all possible upper sums that we have, so for all partitions. This means we will take the set u of fp, where p is any partition of AB. Okay, so we've seen as the partitions get finer and finer, the previous theorem has shown that the upper sums get smaller and smaller. And since we've seen that they always are bigger than the surface area below the graph, so we want them to get as small as possible to approach the graph as good as it gets. So what we then do is to define the smallest number that we get this way, and yeah, maybe this might not be an upper sum, but we just want the infimum of all the upper sums. So as small as we get, the smallest lower bound for all the upper sums. And this is what we call the upper integral, and this is at the moment denoted by AB with an upper bar over here, f of x dx. This integral notation is actually really historic and a bit weird from today's point of view, but I will say more about this maybe in a second. This is the upper integral now. So this integral sign, which looks like a butcher's tool where you can put a kind of hang a pig on or whatever, which you can hang on a stick. But anyway, from A to B with this upper bar for now and this dx behind the function that we consider here. Okay, then in the same way we do the lower integral. The lower integral of f is the following. We now take all lower sums over all possible partitions of our interval. So, and now we know that the lower sums are always smaller than the surface we are searching for, but the finer we get, the bigger these lower sums get. So the bigger and bigger approximating this thing. So what we want is now the supremum, the smallest upper bound. And this is called the lower integral, and this is denoted by a with a bar below this butcher's tool here. A to b, f of x dx. And now, the question is now, of course, in the example I had, in this graph that I've drawn, the function was nice and continuous, but now, for now it might just be some really messy function. And the question is now, when does this surface area make sense at all? When does it make sense to speak of this? And this is now the idea, this is what we call an integrable function. Namely, f is called Riemann-integrable, a German mathematician from the 19th century. Riemann-integrable, or simply integrable, if it's clear what we're talking about. Later on in Math 3 or Math 4, you will see the back integrable functions. This is a more general concept, but anyway, it's called Riemann integral if simply the upper integral coincides with the lower integral. So integral, lower integral fx dx is the same as the upper integral. So this means from both, we are approaching from both sides and get the same value, so then it makes sense to speak of this value. And yeah, in this case, if this exists, we just call this value the integral. Then we just leave out the bars and just denote this by this Butcher's tool from a to b, f of x dx. This is then simply defined as the upper integral or the lower integral, which doesn't matter here at this point. F of x dx is called the integral of f over ab. Okay, b and c, just the definition. Just to save some notation, let me denote this curly r. So this is an r like Riemann of ab should just denote all the Riemann integrable functions. So, and keep in mind, by assumption, f is bounded. So every Riemann integrable function is bounded. F from ab to r, f is Riemann integrable. Okay, so much for the definition. Let's do some very simple examples. Okay, the first one is really simple. Okay, if I ask you for a bounded function, this is kind of the most simple example you can find. Let f go from some interval ab to r. F of x is c for all x. So some constant function. So for some value c in r. Okay. There it's not very exciting because if you take a look at the graph, let's say here c, we have some interval from a to b, so the graph is just this, and so this area here of the surface, this is just a rectangle. And every lower sum and upper sum is, yeah, this is nothing interesting because we decompose this into rectangles and just have a union of rectangles whose union is the big rectangle. So it's not very exciting, but just let us prove this. You can easily see, since yeah, the formal argument for the lower sums and upper sums, you need the infimum and supremum of the function over an interval, and here infimum and supremum are the same. It's just always this value c. So for all partitions, p in, so let's denote this by x0 to xn again. Partition of a b. You get that the upper sum of f over p is the same as the lower sum of f over p, which is just simply the sum from 0 to n minus 1 c times xj plus 1 minus xj. But we can just take this constant value and pull it out of the sum. Then we would have just this sum here, we would just get into this telescopic sum, and the endpoints of the partition, so this has to be a, this has to be b by definition of the partition. And so this means that this is the same as c times b minus a. And this then implies, because then we have that this set here only has one element and this set only has one element, so the supremum and infimum coincide. And we get that f is Riemann integrable with integral ab f of x dx. So you can also write this as integral ab c dx, of course. This is c times b minus a. Okay, as easy as it gets. Now, you might think, okay, this procedure of taking lower and upper sums, this looks wonderful and looks like it's always going to work. Let's take an example where it's not working, or where we don't get a nice proper integral, properly defined integral. We take the function which goes from the interval 0, 1 to r, which is defined in a funny way. F of x only has two values, 1 or 0, and we say it's 1 if x is a rational number, and 0 if x is not a rational number. Okay, this is some function that is impossible to draw because we have so many different values here, so it's kind of, yeah, some 1 or 0. But we have seen before that every non-empty open interval contains both rational and irrational numbers. A non-empty open interval contains elements of Q and of the complement of Q are without Q, irrational numbers. But this means we always take the supremum and infimum in these partitions of the values of f over some non-empty interval. But this means the supremum will always be 1, because there's always some point where the function is 1, and the infimum will always be 0, since, yeah, there's always a point where it gets 0. So, whoops. This means, if we just write this down, hence for all p from x0 to xn in the partitions of AB, we see that the lower sum, because all the infima are 0, this is the same as the sum from j from 0 to n minus 1 of 0 times xj plus 1 minus xj, which is obviously 0. But u of fp always takes the supremum, which means that this is the sum of 1 times xj plus 1 minus xj. This is again a telescopic sum, and this is then the difference of the endpoints of the interval, which is 1 minus 0, so it's 1. This is for every partition. They are all, the lower sums are all 0, the upper sums are all 1. So again, here we have some sets which have one element, but they are different sets. So in this case, we get that the upper integral from a to b f of x dx is 1, but the lower integral from a to b f of x dx is 0. And so this means f is not Riemann integrable. So this is the kind of most elementary example of a Riemann integrable function, a non-Riemann integrable function. Okay, we have to study integrals further, and we will go on with some properties of lower and upper sums and lower and upper integrals.